moment you're interested in the parameters that describe their distribution, so like luminosity functions here, halo mass functions, and so on. And I'm looking right now for examples to throw that which are easier than lensing. Good, so that's the last point I wanted to make, so these are my conclusions. Radio searches for axion dark matter provide right now the strongest constraints above masses around a couple of tens of microelectron volt, and significantly stronger than other probes. Even for core dark matter profile, this actually looks quite good. And yeah, since there's just lots of sensitivity of radio observations will massively increase in the future, there's still, I think, still lots to gain. Differentiable programming, I try to give you like an idea of what this is. In my opinion, opens up lots of new avenues for actually modeling data and solving high-dimensional complex data analysis problems. And it's effective, it's fast, and one can take over lots of the technology that was developed for deep learning to like problems that are more closer to what we are traditionally used to do. And yeah, what I'm very happy about is this, that the fact that this maximum entropy maximization on the model level actually seems to lead to reasonable results, which basically get you around of actually having to sample or marginalize the posterior. So you just approximate in this way the marginal posterior and can get anyway information about population properties. Yeah, that's all I wanted to say. Thank you. And I'm sorry, I'm a bit over time.
And you skipped the third half of the talk.
I cannot stay.
So before we run off to line up for sandwiches, any quick questions?
So then you will have dn over dn to be gamma 1 minus 1.9. There are also other fits that in some cases they are indistinguishable from each other. So I wanted to know, did you check, because there were also some cases that they were not completely matched with your mock data. So did you check if you just reduce it, like increase it to 1.7 or whatever, do they give you a something better fit or?
Yeah, I should say we are still quite far, I'm not sure how far, but we are still not at the point where we started to systematically study sensitivities or so. So this is basically one of the pieces in the puzzle of getting an analysis pipeline working to study subhalo mass functions. Right now, what we do here effectively is to generate subhalos that roughly follow this distribution with some cutoff at some point, and then at low masses also we have to introduce an artificial cutoff. And the kind of challenge is that if you fit the cutoff of the subhalo mass function, you kind of, if you change the cutoff, you change the number of halos, right? We can't change the number of degrees of freedom objects in this kind of scheme. So what we do right now is if we go to low masses, we just smear these halos away. So that the advantage is the overall mass of the substructure is not removed. So we still keep, like on large scales, the mass that was there before, but we remove the effect of some small halos on the lensed image. So that's kind of the state where we are. In principle, all these things like studying different mass functions and so on are relatively easy to address once we can solve the statistics problem of constraining them in the first place.
I'm just curious, like, I guess I was naively thinking that variational inference might work for a problem like this. Like, could you explain a little bit, like, what were the pitfalls?
No, I mean, it worked in the sense that we get the lens parameters very efficiently back. It's quite nice. The only problem is that it's kind of solving the wrong problem. So in the future, the problem is not to get the lens parameters super accurately, but to actually have a source model that is good enough to account for highly resolved, low noise image and basically get the smoothing scales of that correct so that we can on top of that see substructure. And using this variational autoencoder runs into the problem that it's still very opinionated about how galaxies look like. I mean, it's just 64 parameters for image with like 64 more pixels. So the basic problem is if we decrease the error bars, we usually get residuals that look very large. And probably one could avoid this by making the autoencoders a lot better, but Gaussian processes are much nicer.
All right. right, well, Christoph is around today and tomorrow, so there's still spots on the schedule tomorrow. So let's thank him again.
Thanks.